Good afternoon, everyone. I am Marshall Kern. It's my privilege to be the volunteer president of the Bowman Center for Sustainable Energy. The Bowman Center for Sustainable Energy is based in Sarnia, Ontario, and is a federally incorporated nonprofit organization with about 24 associates across Canada. We are focused on trying to find and support and catalyze big energy projects to further Canada's future energy strategy. Our office is in Sarnia, which is on the traditional territories of the Three Fires Confederacy. This afternoon's presentation is turning over our time to Carbovate, a development corporation who has a, an additional opportunity to explain to everyone regarding alternative flare systems or flare alternative system. To lead you through the rest of the presentation, I turn to Ed Brost. Ed, please begin.
Thanks, Marshall. So this afternoon, we're going to talk about what we call the Carbovate Flare Alternative System, or FAS. We were granted some patents on this earlier, 3 patents earlier this year, which frees us up now to talk about how this system works. The system incorporates what might appear to be magic. And so we're going to be talking a little bit about magic today, and we're going to talk about our plans or strategy for commercializing this innovation. But before that, I would like to introduce our audience to Carbovate. So Carbovate Development Corporation was founded in 2018. We have associates we're a Sarnia-based company. We have associates in Toronto and Quebec, as well as in British Columbia. And like most corporations, we have a nice flowery mission statement, but it can boil it all away. What it really means is, what can you do with bitumen besides burn it? And I'm referring here, when I talk about bitumen, I'm referring to Alberta oil sand or Western Canadian oil sands bitumen. Most bitumen today that's produced or extracted is converted into fuel, and we burn it. The world's changing though, and as the world changes, we're looking for ways that we could use this bitumen as really valuable resource in ways that don't involve combustion. In other words, bitumen beyond combustion. To that end, Carbovate has been involved in carbon fiber research for the last couple of years, but we're working also on an even sexier product than carbon fiber, and that's asphalt. As it turns out, asphalt or bitumen is, depending on the lease, the source, somewhere between 60 and up to as high as close to 80% asphalt. Now, today, that asphalt is primarily converted into fuel and burned, but this asphalt is actually some of the best asphalt in the world. And in trying to come up with a way to extract asphalt cheaper than it is today, we developed an entirely new process to extract asphalt from bitumen, and we were granted a patent for that process. There are a couple of, actually 4 variants of this asphalt process, and one of them though features zero scope 1 or zero GHG emissions at the source and minimal scope 2 emissions. Now you can imagine that for a process that depends on a flare, this is kind of a challenge. What do you do about the emissions associated? You can't go claiming near zero if you have a flare. And so we spent a lot of time and effort and money developing a process that eliminates the need for a flare for our process. What the flare does in the event of emergency or maintenance, the process will capture and reclaim rather than burn and emit the material. So that's a bit of background about Carbovate and why it is we're before you today talking about an alternative to a flare. Now, before we go much further, we need to be crystal clear. This is not a solution to all processes that need a flare for protection, for safety. This process that I'm going to describe to you today is well suited for processes handling fluids with boiling points above, say, ambient temperature. And that includes solvents, gasoline, chemicals like benzene, toluene, xylene, alcohols, and so on. And that type of material, this system should work very, very well. It's not compatible, or that wouldn't work very well at all, with processes that have a high inventory of gases or what we call non-condensables. So materials that have boiling points, say, below 20 degrees C, and that would include like liquefied petroleum gas, propane, that sort of thing. Having said that, this process could work regardless of the inventory in the plant when it's operating, could be used for maintenance or support services, even though the process might normally be processing a lot of hydrogen or methane or whatever. So we'll talk a little bit more about this maintenance application later today. So we are standing before you, or sitting before you, talking about some claims about a flare alternative system. And I just want to highlight again that it's patented and it could be a substitute for certain processes. It is completely passive. This thing, once it's in operation or once it's in service, requires nothing to operate. Pardon the double negative, it almost can't not work. The material, as I said in the outset, it captures material for reprocessing and sale. The containment vessel is reduced. Something like this, you might, oh, you're going to need something the size of a hockey rink. Well, it won't, because of the chemical properties of the operating fluids, which I'm going to discuss in some detail. This process, this carbovate FAS is really suitable for protecting a single process units or perhaps several process units in a large facility, not likely for the entire facility. And if your company is interested in managing GHGs, this is a solution for certain processes to mitigate GHG and conventional air pollutant emissions associated with a flare. So with that, we are talking about substituting an inherently a critically important safety device called the flare. This is an extraordinary claim. And like Carl Sagan said, extraordinary claims require extraordinary evidence. And so towards some of that evidence, we have hired a couple of independent engineering companies to build simulations for us. These companies are independent. They're not even in the same country. And so they have developed the simulations, and the simulations work. It shows that the thermodynamics, heat material balance, all of that, this actually works according to the models. To that end, we were granted, as I mentioned earlier, 3 patents describing how this process works. And we are working with Patent Cooperation Treaty, PCT, and the PCT has taken an initial look at our claims and validated all of them. They say, first of all, they're credible. Nobody else is doing this. They are unique, and they told us that in their view, this idea has commercial application. So with that, I'm going to tell you now how it works. How does the carbovate FAS technology work? So this is a kind of a complicated looking diagram, but we're going to go through it one by one, because at the end of the day, the way this thing works is incredibly simple. It looks complicated, but as I said, we're going to be walking through most of these lines in the next 10 or 15 minutes or so. I mentioned magic. The way this thing works depends on some physical properties that we all need to understand. So bear with me. It's a review, I'm sure, for most people, but we are using something we refer to as a low vapor pressure fluid as part of how this thing works. And what do I mean by vapor pressure or vapor pressure fluid? Most fluids, all fluids, exhibit a vapor pressure. Water in a glass is emitting in the water vapor, and inside the glass is going to contain more water in the vapor space in the glass than in the air around you, which also contains water vapor. Oil has a very low vapor pressure. And when I say oil, what I'm thinking of is think of new motor oil or vegetable oil, olive oil, cod liver oil, that kind of oil. A fluid that has a boiling point of a couple of 300 degrees C, something like that. So at ambient conditions, that material has almost non-detectable vapor pressure. There's no such thing as zero, but it is really low. In contrast, look at we have a component in this system called a high vapor pressure fluid. What we mean by that is a fluid relative to the oil has very high vapor pressure. Now think of a can of gasoline in the summertime. When you open the lid, it goes poof, because that's due to the vapor pressure of the gasoline. So for purposes of our discussion this afternoon, our high vapor pressure fluid will be something like naphtha, which is, think of camp stove fuel or lighter fuel or something like that. It could, or solvent, paint thinner. And if that's, think of rubbing alcohol, something like that. Something has a boiling point maybe around 100 or 150 degrees C, so that under ambient conditions, it's relative to the oil, exhibits a significant vapor pressure. So what we have here is a cartoon. There's our vessel, the heart of the system. And over here, we have the protected equipment and a relief valve. So let's see how this thing works. We're going to simplify it and get down to the how do we start it up? Well, here we have our brand new vessel delivered to your site on a truck. Of course, the vessel is steel and it's full of air. And so what are we going to do about that? We don't want any air in our system. Just we're going to start and open some valves. Excuse me. And move some oil into the vessel, displacing all the air. So now we have a vessel with no air in it, and the excess oil has gone back to storage. So now we want to create a vacuum. Now we could have used a vacuum pump and sucked the air out of the vessel, but it won't be a perfect vacuum, not like what we're going to have here. So instead of a vacuum pump, we're going to create our vacuum by using an oil pump, which is much more efficient than a compressor anyway. And we start running our pump, but our pump's not going to run for very long. Why? Because we don't have, this material has no vapor pressure to speak of. So we're going to end up with a bubble in the top of the vessel that is occupied by oil vapor. And it's going to be under a very deep vacuum. It's going to be equal to the vapor pressure of the oil and the temperature and pressure, which is ambient inside this vessel. That's good news so far because we have a deep vacuum. And remember, in our busy cartoon, we had the protected equipment over here. So if something happened, the good news is it's going to flow very rapidly over here. The bad news is the bubble is so small, the vapor space is so tiny, it doesn't have much capacity to collect and capture relieved material. So what are we going to do about that? Our pump, in fact, is going to, it'll stop running, it'll sputter, it'll cavitate. So what are we going to do? We're going to inject our naphtha, our high vapor pressure fluid, into this same space. So we open our valve, the naphtha flows in, but guess what? Under the conditions in here, this material is way above its boiling point at 20 degrees C. So it immediately flashes into a gas and evaporates. And that means it increases the pressure a little bit, allowing our pump to start again. So now we can pull more oil out and add more naphtha. And while this is happening, the pressure is staying under vacuum. It's still staying under vacuum. Now, there's one last physical property of these fluids we all need to be clear on. So when you evaporate a liquid from, say, into a vapor, the vapor occupies far more space than does the liquid it came from. In the case of light hydrocarbons, like we're talking about, notionally, 1 liter of liquid will form about 200 liters of gas vapor. The exact volume depends on a bunch of variables like temperature and pressure and other factors, but notionally, it's far more volume involved. In the case of my discussion here, saying 200 liters of gas will come from 1 liter of liquid. So when we get to the armed state or ready state, we'll have our vessel full of naphtha vapor, tiny little infinitesimal amount of oil vapor in here because it doesn't have any vapor pressure. The system is under a vacuum, and we now have physically an apparent volume that's much more significant in context of being able to collect relieved material. So far, so good. So back to our busy cartoon. We have our protected equipment. We have our vessel here with the naphtha and oil in it, and that is called, we refer to that as the armed state. The system can now be disconnected from all of these connections because it doesn't need anything else now to operate. And this is where something that might appear like magic happens, because as Arthur C. Clarke said, any sufficiently advanced technology is indistinguishable from magic. And you might have noticed that some of the color cartoons and highlighting were in purple. That's the magic part. So here we are. We're under vacuum. Let's focus in on this part of the system now and get rid of all the other lines. And what we have is our protected equipment. We have our vacuum vessel or our containment vessel in the armed state. And we have a pressure or relief header analogous to a flare. Now, normally in a normal system or a conventional system, this relief valve would be connected to your flare. Here, it's connected to the containment vessel instead. The pressure safety valve, if it is here, and if the pressure in our vessel, for whatever reason, exceeds a target number, the valve will open and go either to flare or in this case to our containment vessel. So we have some kind of an event happened. The pressure it starts to increase. It gets to an unacceptable level. The relief valve opens. It go the overpressure material then flows toward an optional cooler. It's not necessary, depending on the process. We may or may not need that, but this is a passive cooler in that it is just a bunch of tubes with fins on it. So it's an aerial cooler, but with no fan or anything like that. The cool material then flows in here, and this is where the magic happens. Remember, I said 200 liters of gas forms 1 liter of liquid. Well, as this material goes in here, guess what happens? The pressure starts to rise. This was at equilibrium before the valve opened. And so what's going to happen is some of this naphtha is going to start to condense. And as that happens, for every liter of naphtha that condenses, it frees up 200 additional liters of space to accept material from our threatened equipment. And so if you can envision this, before the relief valve opens, everything's in equilibrium, it's nice clear blue sky or whatever color, yellow sky inside the vessel. Once this opens up, it'll get very foggy, and then suddenly it'll start raining naphtha inside the vessel. And so although the vessel is steel, it's not a balloon, it's the tendency here is for not only the volume, but also the pressure to be sustained. The volume will go up, especially because the liquid's rising, and the pressure will also rise slightly, but the vacuum, there is a very strong tendency for the vacuum, the pressure, and the volume to be retained, even though there's more material flowing in here. So we have more kilograms in here, but like magic, everything seems to be staying the way it was prior to the event. So now we have the event is over. The pressure has been restored. The fire is out, or whatever was causing the disturbance. The relief valve closed. Flow was suspended, and here we have nothing went to a flare. Nothing was released. Everything is now contained inside our vessel. It's sequestered, and so we are now going to recover that material. This gets really easy because we're going to do the same thing we did when we commissioned it in the first place. All we're going to do is open our valve here and send oil into the vessel and fill it up, displacing everything that was in the vessel, including all the material that was captured from our threatened equipment. And it can go back to storage and eventually for reprocessing and sale. So what I've described for you is something is referred to as a passive self-regulating process. This thing doesn't, as I said, it doesn't need any electricity to operate once it's armed and in service in his role as guarding this equipment, the protected equipment. It doesn't need electricity. It doesn't need steam. It doesn't need fuel. It doesn't need anything. It doesn't even need an operator. This thing, all it has to happen is this relief valve. If the pressure gets high, all it has to do is open. Everything else is automatic. And so it is completely passive in its operation. And so this applied, now we went to a lot of trouble around this applied magic to figure out how this could all work. And there's a reason for that. You could have a system like this without the applied magic, but the vessel will be huge. The purpose of this combination of fluids is to reduce the size, the physical size of this vessel. It doesn't need to be very big at all compared to a vessel that was just depending on its physical, mechanical, if you like, volume as defined by the vessel itself. So that leads us. So we have this technology. It's an innovation. We have patents. We've done some, as I said, some modeling to see that it works. But this is the innovator's valley of death. And on the left side is where you have the invention, and on the right side is where you have its commercial. And we're over here somewhere. One other thing we've done towards getting across this valley of death is we've had an external engineering company physically design a plant, of FAS to support our asphalt plant. And so what we have is process flow diagrams, P&IDs for the entire facility, the sizes of the vessels, the supply and control P&IDs, auxiliary equipment, it's all there, all giving us an opportunity to get a capital cost for this thing. So we also have, in an interest of commercialization, some notion of what a system like this would cost. So this is the next is cartoon is about an engineer's version of the Valley of Death. And what we have here is the government funded research. Now, Alberta Innovates has been a sponsor and has helped us with development of this technology, but that's not the same thing as being commercially viable. So where are we in our journey across the Valley of Death? I think we're somewhere around here. We've done the academic work. We've got the process simulations. What we have is evidence that from a thermodynamic and heat material balance and all of that, that this thing works. We don't have any lab research conducted as of yet. Now, this is a very difficult technology to try to demonstrate because of the role a flare plays in a plant. It is primarily and fundamentally a safety device. It is there to protect against overpressure circumstances, and you would be loath to put, or you shouldn't put a prototype in that kind of service and not have a flare until it's proven physically. And so that is what we're trying to do. We're trying to get across this valley of death. Now, we have a strategy to try to de-risk this physical demonstration of the technology, and that is around planned maintenance. Because although a flare's primary objective involves safety, flares are also used as part of planned maintenance. Under completely controlled conditions, material is relieved to a flare, and we think that is how we could. That would be one of the first steps. Actually, the second step in getting across the valley of death. So how would that look? Well, in any ordinary facility, petrochemical facility that's being shut down to be ready to be open so people can go in the vessels and experiment or inspect them and do maintenance repairs or whatever, the first thing to do is get all of the hazardous material out of the vessel. And the way that's done is using your blowers, pumps, compressors, whatever, to evacuate or de-inventory the vessel, the equipment. That method only can go so far. There still will be residual vapors and gases and pockets of material and sludge or whatever inside the vessel, and it's not safe to open. So the practice is to, as I showed in an earlier slide, there is a bypass around this relief valve. So what you can do is with the valve closed, you can open this valve. I'm getting ahead of myself here. And normally this would go to a flare. You'd steam the equipment out to a flare until safety department says it's safe to open. In this case, what we're going to do is we're going to put steam in it exactly the same way and with no undue risk. And it goes through our bypass, through our cooler, into our vessel. Now, water, I may have mentioned this earlier, I forget, but water is a high vapor pressure fluid compared to the oil. The water is going to behave in there just like the naphtha does. So as the water flows in there and the pressure starts to rise, it'll begin raining naphtha inside the vessel, just as it would in an emergency scenario. But also, this water is also going to condense and sustaining the temperature and pressure in the vessel. And so you can do that until the equipment is determined by the safety department that it's safe to open and enter. So that's how you could use this equipment in a maintenance support role. And in this role, it wouldn't matter if the material, if it was a hydrotreater, wouldn't matter if it was the operating process uses a lot of gases or non-condensables. Before we go a little further, I've been talking a lot about flares and I've talked about the difference. So I'd like to differentiate on one page what we're talking about here in terms of the advantages, disadvantages. So what we have, if you're interested in GHG emissions, if that's part of your concern, then the flare, which was a complete obstacle for us until we come up with this idea around getting to scope 0, scope 1, or scope facility emissions for our plant. Flare has that, especially if it has a pilot, it's going to have GHG emissions chronically all the time. That's not the case here. In the case of if there's an emergency relief or even a planned maintenance release, again, more CO2 on top of the chronic. This is an acute event. It doesn't apply here. Flares are not particularly good combustion source. They're not really good at it. There's a lot of combustion, like a furnace is much better at burning the fuel than a flare is. So you end up sometimes with smoke. You end up with SO2, NOx, particulates, VOCs, all kinds of other things that are coming out of this flare. Again, not an issue with our system here. Flares, unlike this system, which is very simple, flares are actually, they look simple, look like a candle, big monstrous candlestick, but in fact, to make them reliable, and they are very reliable, because there is a lot of equipment that's involved in maintaining or ensuring the reliability. Pilot flames, igniters, monitoring equipment. If the flame goes out, a flame front generator, if the igniter doesn't work, there's all kinds of stuff that is active. None of that is required for this. The steam to help ensure combustion, steam is usually supplied to a flare. That's not required here. There's no power supply required once it's maintained, but there is here to operate all of these ancillary equipment that's required to make this thing as reliable as they are. If you have an emergency event in a flare, the temperatures at the ground around the flare get really high, dangerously high. So it's something called an exclusion zone, that when the plant is in operation and being protected by the flare, you cannot enter the exclusion zone. That doesn't apply here because there's no flame. And again, the material is recovered here, not so here. So that's enough. We won't go any more time on this. There's a whole bunch of advantages here in this that offers this. So there's a lot of motivation on our part to figure out a way to make this thing commercial. The potential applicability, most of the people in Carbabate, along with some financial people and marketing people, most of them our experience lies in the petrochemical industry, refineries, and in the oil sands. And here's a listing of some of the types of equipment that would be suitable candidates for this kind of technology instead of a flare. There are also in the chemicals and beverages sectors, like in beverages, this will work perfect in a distillery. Water could be one of the fluids, as well as the ethanol. Alcohol plants like methanol, ethanol, propanol. There's all kinds of industries in the chemical sector that this technology could serve. One of our consultants has connections to the pharmaceutical industry, and he has told us that he thinks there are a lot of applications in the pharmaceutical sector for this type of work. Now, if you ask me a question about the pharmaceuticals, I'm just going to tell you our consultant said so, because I really don't know. I can't really make any more comments on that one. So in summary, Carbavate is offering an alternative to a flare system. If you're concerned about GHG emissions, this could represent a path to mitigate one of the more challenging GHG emissions in the facilities served by a flare. If you were in a facility that has a flare and the flare is limiting, you'd like to expand or put in a new process unit, but the economics around that have to include debottlenecking or building a new flare. This offers a way around that. Even if the grand idea involves gases or non-condensables, what you could do is apply the Carbavator FAS to some other facility in the plant where it is suitable, which would free up capacity on your flare system. Because there are no emissions, no noise, no light, none of that, we think that this technology would be seen, the stakeholders in the community would see this as a friendly approach. And if that turned out to be true, then there's potential for fast track regulatory approvals. So next steps. So we are looking to partner with us to build, a lab or a pilot scale unit to demonstrate the concept in a tangible way. It's already been demonstrated with models, but physically. We have got some reasonably good plans on how that lab test would work and what it would look like. Once that's proven to work, then the next step would be to build a commercial demonstration unit. And in this case, I think the demonstration unit would probably be sized so that it could fit on a trailer or maybe two trailers or a truck. Think of a vacuum truck. And then you could go to a whole variety of different industries and try it out in their as part of their maintenance operations and shutdown operations. And doing that, we would test a whole variety of potential applications without presenting any undue risk to anybody. To that end, we are engaging with potential investors and regulators to help us with our journey across the valley of death. The type of people we're looking for are likely maybe multinational corporations with connections to the oil and gas and petrochemical sectors. So with that, I'd be glad to entertain some questions. Am I talking? Hello? Hello? Ah, there you are. Hi, Marilyn. Oh, Dawn, can you unmute Marilyn? Dawn Greaves.
I'm never surprised when they don't want to unmute the politicians, but so excellent presentation, super interesting idea. One of the challenges I see is that flare events, they've got a huge range. Sometimes it's a little, sometimes it's a whole hell of a lot and way more than you think. You've got a small vessel for, an economic cost. How are you taking care of, valve sizing in and out to ensure that in a super rapid event, you can bring that all the gas in and let the oil out while still being responsive in a smaller event?
That's a really good question, Marilyn. And at the outset, I mentioned that this, well, magic things are happening here. At the outset, I mentioned that this would be suitable for a single unit. So we don't think you would take a whole refinery and try to bulldoze the flare and replace it with a vessel like this. No, what you would do is bolt it to the BTX splitter or fractionator. And so it'd be connected to one unit. Your question, I think, also included how do you come up with the line sizing over to the vessel? Well, that would be the same as you do with a flare. You're going to have a header, and a smart mechanical engineer with fluid mechanics expertise, excludes me, but I think would not have any problem with that because we have quite a pressure differential here. We have the vessel is under vacuum, and whereas a flare header might be operating at 10 psi or something like that, some marginally above atmospheric pressure to ensure you don't get air in it. Here we have more motive force because we have it under vacuum. So I don't know if that answers your question. I think though thank you. A key though is we're not we're not thinking that at this point this thing is ready or whatever likely ever be appropriate to take down the whole flare. It's going to be for one unit. Now in a refinery, you might have like an alkyl unit, and a deisohexanizer, and a BTX distillation column. That would be three of them, one in each unit. Yeah. Okay. Everybody's muted, Don, so maybe that's part of our problem.
The way, sorry, the way we're doing it is if they have questions, they should use the chat function like we've done before. And yes, but just well, I have a question. Is if you go back to basically your flow diagram, and I would call it a pretty complicated flow diagram, does it necessarily have to be that complicated?
No, the diagram is that complicated.
Could you go to the diagram?
Could take it up? There we go.
Yeah, there we go. Okay.
Yeah, so this diagram is that complicated so that I could take these lines apart and show you how, so it will enable easy explanation of how this thing works. But in fact, if as a chemical engineer, if you know the pressure in here that you want to get, and you know the temperature because it's ambient, then you could come up with a cocktail of fluid that is already at the right mixture here, so that all you can eliminate this, you can eliminate this line here, this line could be they could all be one line limiting all these valves, and only have one pump. So it could be including this one down here. This could all be part of the same system. If you had a cocktail, I'll make up the number for illustration. It's 10% naphtha and 90% oil, and if you stick that in there, by definition, through just physical chemistry, you're going to end up with the right amount of oil at the bottom and the right vapor pressure, right amount of headspace in the vapor space, and at the target volume, because those conditions are actually defined by the composition of the mixture. So thanks for the question. Yeah, this could be a lot simpler, but I needed it because I wanted to be able to take the different parts of the drawing out to show you how each, it would have been much more difficult for me anyway to explain how this works if I use this cocktail to try to explain how it works. Thanks, Don, for that.